Let's try to solve this problem here. A copper wire LM is fused at one end, M, to an iron wire MN as shown in the figure below. So you have your copper wire LM and it's joined together with another wire made of iron, which is MN over here. Okay, they tell you that this copper wire has a length of 0.90 meter. So copper wire is LM. LM here has a length of 0.90 meter and cross-sectional area of 0.90 times 10 to the power negative 6 meters squared. So let's write it down. Okay, so your length over here will be 0.90 meter. Let's call it as the original length of copper is equals to 0.90 meter. And they tell that this copper wire also has a cross-sectional area of 0.90 times 10 to the power negative 6 meters squared. So this will be the area of copper, cross-sectional area of copper, 0.90, sorry. 0.90 times 10 to the power of negative 6. Okay, that's for LM. Okay, continue. The iron has length of 1.40 meter. Iron is this one over here. MN has a length of 1.40 meter. So let's write it down as well. So LO for iron. Iron is Fe, right, in chemistry. So this is 1.40 meter. And they say that the cross-sectional area is 1.30. Cross-sectional area of iron here will be 1.30 times 10 to the power of negative 6 meters squared. Okay, so this is the cross-sectional area over here for this wire. If you cut it over here, then you measure the area that you see. This will be the cross-sectional area. Okay, the compound wire is stretched and the total length increases by 0.10 meter. So you are going to apply a force on both ends of this compound wire. So you are going to stretch it with equal forces experienced by LM and also MN because they are stretched by the same force. Okay, and the total length increases by 0.01 meter. Total length increases by 0.01 meter means by there are some portion of extension that happens to LM. You don't know how much. There's also some portion of extension that happens to MN, which you also don't know how much. But you know that the total amount of extension that happens for this compound wire over here will be 0.01 meter. That's the idea. So you don't know how much extension experienced by copper. You don't know. You also don't know the extension that happens to iron, how much does it extend, but you know that in total, the amount of extension that happened will be 0.01 meter. So that's the idea that they are trying to convey here. Okay, so determine the ratio of the extension of copper wire to the extension of iron wire. So for this situation, they are asking for what is the extension. Extension is change in length of copper to the extension of the iron wire. So delta L of Cu divided by delta L of the iron. Okay, so I think you're given a lot of information. You're given the original length, you're given the cross-sectional area. So from this information set being given over here, I think you are able to see that actually the Young's modulus equation will be relevant, okay, because you have the original length, they're asking for extension, that's the strain already, right? Delta L and L together, they form the equation for strain, and you have your area over here, and the force experienced by these two wires are the same. So the force and the cross-section area forms the stress. Then you know that stress and strain together, they are related by Young's modulus, because Young's modulus is equal to stress divided by strain. And actually, in this question, I think they have already given the Young's modulus, which I forgot to copy it inside. So let me put it here. The Young's modulus of iron is 2.10 times 10 to the power of 11 Pascal. Whereas the Young's modulus of the copper is equals to 1.30 times 10 to the power of 11 Pascal. Supposed to be given, I forgot to copy it inside here. Okay, so I believe you see that this Young's modulus equation be relevant because this is why you know it's Young's modulus is stress divided by strain, force and area, you have the information, the extension, change in length versus the original length, you have the information for strain. So most of the things are there. Young's modulus is the way to go. So let's rearrange the Young's modulus equation. You know that Young's modulus is stress divided by strain, which if you expand it is force divided by area for stress. Then you have your change in length divided by the original length for your strain, which if you rearrange it, you can rearrange to become force multiplied by the original length is equals to area multiplied by the change of length. Okay, so right now they're asking for the ratio of delta L against delta L. So maybe we should put delta L as our subject over here. So delta L is our subject. That means you have FL not over AY as our right hand side. Okay, just rearrange this equation. So we are going to use this equation to put it inside here, but because there's two conditions, one for copper, one is for iron, so we need to label everything clearly. So up there we have copper, so you have your force experienced by the copper wire, your original length of the copper wire divided by the cross-sectional area of the copper wire divide also by the Young's modulus of the copper wire. So this is upstairs. What happened downstairs is for iron, so you have force experienced by the iron wire, the original length of the iron wire, you have a cross-sectional area of the iron wire, and lastly you have the Young's modulus of the iron wire. Okay, so this is how you find the ratio between the copper and the iron by rearranging this equation, making the extension as our subject over here. Okay, we know that copper and iron here, they are experiencing the same force because this force is being pulled on both ends. So that means these two wires here supposed to experience the same kind of tension. So this force over here are the same. So because the force experienced by copper is the same as the force experienced by the iron, you know that these two can cancel out, okay, because they are the same. So now you can proceed with a substitution. The change of length of copper divided by the change of length of iron will be equals to the original length is 0.90 for copper divided by the cross-sectional area 0.90 times 10 to the power negative 6 multiplied by the Young's modulus for iron, for copper. For copper. Wait, did I do it right or not? Area, copper, original length, copper, Young's modulus of copper. Okay, you have to be very clear, don't substitute it wrongly. So, power 11. So this is what happens as in the numerator. Let's move on to the denominator. Denominator, the change of length of iron will be, the original length of iron will be 1.40. This is obtained over here, original length of iron, divide by the cross-sectional area of iron, which is this one, 1.30 times 10 to the power negative 6. And also you have your Young's modulus of iron, which is 2.10 times 10 to the power 11. Okay, so if you substitute everything inside and you do your calculation, I believe you'll get an answer which is 3/2. Okay, so that means by the ratio of the extension of copper wire to the extension of iron can be equated to be 3:2. Okay, so this is the ratio between the extension of copper wire to the extension of iron wire. Okay, now you know this. Okay, actually you can rearrange this equation up there. You can rearrange this equation to become delta LCU is equals to 3/2 of delta L iron. Okay, again, I'm just rearranging this equation. I hope you are clear with it. Change of length of iron. So I just bring this to the right hand side. I bring the extension of the iron to the right hand side, and this is the equation I get. Why do I want to rearrange the equation this way? Because now we can proceed to the next question, which is the extension of each wire. So how much is the delta L for copper? How much is the delta L for iron? You have the equation, but you have two unknowns over here. So when you have two unknowns, immediately you can pop up something in your mind, which is simultaneous equation. So you need two equations with the same two unknown. Your unknown here will be change of length of copper and change of length of iron. So what is the another equation? Well, actually we have the equation already. The equation is over here because this equation here also have the same two unknown, which is the change of length of copper and the change of length of iron. So what you're going to do is, for the second question, the extension of each wire, you need to use these two equations here to do simultaneous equation in order to find the change of length of each of the wire. Okay, so let's do question B. Okay, so let's call this equation 2. Let's call this equation 1. So what you're going to do, you are going to substitute 2 into 1. So now your equation will be 3/2 delta L of iron Okay, I'm replacing the delta L Cu over here. I'm replacing it with 3 over 2 delta L of iron. Okay, then I'm going to add on together with the delta L of iron that we have earlier. Then together, if you find the sum will be 0.01. So now there's only one unknown left, so you can proceed to key in into calculator. And I believe if you do everything with your calculator, you get the extension of iron to be equals to, what's the extension of iron? 4 times 10 to the power of negative 3 meter. And once you have obtained the extension of the iron, to find the extension of the copper is just using this value, plug it back inside here to find the extension of copper. So let's do so. So the change of length of copper plus the change of length of iron is equals to 0.01, in which if you substitute in the change of length of iron to be equals to 4 times 10 to the power of negative 3, you put it inside here. Then I believe you'll find that the change of length of copper will be equals to 6 times 10 to the power of negative 3 meter. Okay, so you are able to find the extension of the iron and the extension of the copper by using the simultaneous equation between these two equations over here. Okay, next, the applied force to the compound wire. So now you want to find the applied force that you previously crossed out in the equation for Young's modulus. But now since you have delta L, you have your original L. Okay, delta L for copper is over here. The original L is over here. Okay, then you have an area. To find force, it's just using the Young's modulus equation only. Okay, let's continue. Oops, I don't have an extra sheet. Give me a second. Okay, so now we need to find the applied force to the compound wire. Applied force to the compound wire, you already have your copper Young's modulus. You already have your force applied, and this one is what we want to find. Force applied on the copper wire divided by the cross-section area of the copper wire. Then the change of length of the copper wire divided by the original length of the copper wire. You have everything here except the force, so it's just substitution only. So 1.30 times 10 to the power of 11. Then your force experience is what you want to determine. Cross-sectional area, come back to the copper wire, find the cross-sectional area. 0.90 times 10 to the power negative 6. Change in length of the copper wire. How much change in length do you have? You determine it from the previous question. Change in length of copper is 6 millimeter. So this will be 6 times 10 to the power negative 3 divided by, lastly, the original length of copper. The original length of copper is 0.90 meter. 0.90 meter. Okay, so if you calculate everything, key into calculator, I believe you get the force experienced by the copper wire to be equals to 780 Newton. And because you know that the force experienced by the copper is the same as the force experienced by the iron, because they are stretched by the same tension over here, you know that this force experienced by the iron will be the same, which is 780 Newton. So this is the force, applied force to the compound wire. Okay, so from here you can see that it's always the same equation. It's the equation for Young's modulus, but we have to carefully manipulate the equation to push things that we're interested in to be our subject. And when you're doing ratio question, you have to be very sensitive. What are the same for both of the wire? What can be cancelled out? So if you're very clear what is the same, what is different, substitute your value carefully, do your unit conversion carefully, then you shouldn't have any problem with this question. Okay, so that's it for this question. Thank you very much.